Hi, my name is Margarita Vald, and I'm a security researcher in the field of data protection and privacy enhancing technologies. Today, I'm going to talk about data protection, but before doing so, I want to mention the biggest data breach in the whole United States history, and this breach happened just a decade ago. I'm talking about the Yahoo data breach that happened in 2013, when hackers managed to steal 3 billion customer records containing highly sensitive data. As a result, Yahoo suffered significant financial and reputational damage. In this talk, I will demonstrate an approach for protecting data against data breaches, and in particular within machine learning applications. I will focus on a solution for data protection in the popular decision tree-based models. I hope you all enjoy my talk. In recent years, as part of the AI and data revolution, companies are increasingly collecting and storing vast amounts of data, and in particular, customer-sensitive data. I believe I don't need to motivate much the importance and benefits of high-quality data. But if we want to protect this data properly, the next thing to happen is a major data leakage. This data leakage can happen unintentionally, but it can also happen by malicious attackers who attack our system on a daily basis. So what companies do in order to protect this data? The common practice is to use encryption and store the data encrypted and also encrypt the data while it being transmitted. But the real question, is this enough? And the answer is no, because data is still being stolen because it's unencrypted during processing. And let me tell you a little bit in numbers. So in last year, an average cost of a data breach was 4.45 million US dollars. And it took companies on average 277 days to realize they're facing a data breach. And these numbers are very high. So in the rest of this talk, I'm going to start with motivation and illustrate give you a concrete example to illustrate why the existing treatment for data protection is insufficient and why we are still facing a data leakage threat. Then I'll introduce a new technology called fully homomorphic encryption and show you how we can use this technology in order to protect data within machine learning applications, and I will focus on decision tree-based models. And then I'll conclude my talk. So to understand why there is still a problem, we need to understand how enterprise architecture looks like. In enterprises, the architecture is the following. We have many data producers that all collect data and store this data encrypted in a centralized storage called the data lake. And this data is encrypted with the standard AES encryption. On the other hand, we have many data consumers that all access this data constantly and use it to perform computations. Okay, so how it works, a data consumer accesses the data lake, fetches the data, decrypts it, it has the decryption permissions, and uses the clear text data for the needed computations. And the problem with that is that it's enough for an attacker to compromise one of these data consumers in order to get full access to the whole data lake, because all of these consumers has access and permissions to the clear text data. So this situation is problematic. We have here a huge vulnerability and a very big attack surface. And actually, this is how many of the data breaches happen, because attackers compromise and take a hold of a machine of an employee and exploit the permissions that this employee has in order to steal the databases, passwords of the customers of the company. And what we want is actually to somehow have a solution that won't enable the attacker to, by compromising a single entity in the system, getting the whole data. So I want to propose a solution that based on a new technology called fully homomorphic encryption. This is a privacy enhancing technology that enables us to process data without decrypting it. What it means is to perform computations on the encrypted data without the need to decrypt it. So let's see how we can use this technology in order to solve the problem in the previous example. So now the data producers will store the data encrypted using this homomorphic encryption. And the data consumer will no longer have the ability or permission to decrypt the data. They will fetch the data encrypted and use it in its encrypted form and perform the computation over the encrypted data itself. And this is supported by this type of encryption. So now, if an attacker compromises and attacks one of these data consumers that are working over encrypted data, he will see only ciphertext. He will not see any clear text data, and therefore he won't learn anything on the data in the data lake. And this guarantees a data secrecy, that we manage to maintain the data secrecy. And by moving as many as possible data consumers to work over encrypted data, we can significantly reduce the attack surface, and we will have only a small set of entities that have permissions to access the clear text data. And I want to further motivate the use of fully homomorphic encryption. It's not only valuable to protect data from malicious attackers, but it also enables us to utilize data that otherwise cannot be used due to compliance or regulations. And I want to give you two examples here. One example is sensitive health information. So it's very valuable for the drug industry, but by law, it cannot be disclosed. And another example, very similar, is tax data. Tax data by law cannot be accessed outside of the United States. So any company that dealing with tax data needs to actually maintain a dedicated team within the United States that will do all the processing related to this data. And this actually results in a very big burden and friction in all the processing involving this data. So how homomorphic encryption can help us here? So now we will be able to use this homomorphic encryption on and encrypt the data, this sensitive health data or the tax data, and work over the encrypted data without violating regulations. We will perform all the computation on the encrypted data without the need to access the clear text data, and eventually we will only need to decrypt the final result of the computation. So now we can still be compliant, but utilize and gain the benefit of this data. Okay. So what is exactly homomorphic encryption? It is type of encryption that allows us to compute functions over encrypted data and obtain an encryption of the computation result. So concretely, we can add and multiply encrypted values by adding and multiplying the ciphertext themselves. And each such operation will result in a new ciphertext containing the result of the performed operation. So, for example, here we have an encryption of a value A and encryption of a value B, and I can add these two ciphertexts and get a new ciphertext that will contain A plus B. And the same for multiplications, which is very interesting type of guarantees, properties that an encryption have. Usually, if we take classical encryption and add or multiply, it doesn't give us anything. So I want to actually tell you that the good news is that every computation can be done over encrypted data, because every computation can be translated or represented as a sequence of additions and multiplications, and therefore we can perform it over encrypted data, over encrypted inputs. But this sequence might be very long. For example, for square root function, it's very long, this sequence. And it means that for certain functions, this computation becomes very inefficient or even impractical. So it will be a challenge when we want to come up with algorithms that will operate over encrypted data. It will be a challenge how to make them both efficient and also how to make these algorithms to contain only additions and multiplications, but in a way that it will be efficient, still efficient. A number of operations won't be that big. Okay, so our goal, as we already said, is to develop machine learning capabilities over encrypted data. So what do I mean? I want to use this technology of fully homomorphic encryption to protect the data within machine learning computation. So what I need to do is to come up with machine learning algorithms that are compatible with fully homomorphic encryption. It means that these algorithms need to that the operations in these algorithms needs to be addition and multiplication, and in this way I can run them over encrypted data that is encrypted with fully homomorphic encryption. And I'm going to show you what we did for decision tree based models. This is what I'm going to show you is part of the results that we achieved and published in a conference a few years ago. And we did it for decision trees, both for prediction and also for training. We proposed algorithms for both of these tasks. We used fully homomorphic encryption to encrypt the data, and by doing that, we achieved privacy for the data. And this means that we needed to have algorithms that are only additions and multiplications. So instead of coming up with new algorithms, what we did is we took, in a sense, we took classical algorithms, identified the operations that are not comparable with homomorphic encryption, and replaced them with a sequence, with an equivalent, somewhat equivalent sequence of additions and multiplications. And we had several challenges there. One is to do it in a way that will preserve the accuracy of the machine learning algorithms. So both for inference and also for training, we needed to get as good results as the classical algorithms will give us. And another challenge was to have the overhead, the running time overhead, minimal as possible, because operating over encrypted data is much more costly than operating on clear text data, and especially if we have many multiplications in our algorithm. So there was a challenge to actively minimize the number of multiplications while preserving the accuracy. So let me tell you how we did it for decision tree inference, and I will show you it somewhat high level, but I will give you all the key insights. So what is a decision tree evaluation? What is a decision tree? It's a binary tree where in each node, besides the leaves, we have a threshold and an index. And in the leaves, we have our labels. So in order to evaluate a decision tree on an input, we're given an input. Let's say it's a vector where each entry in the vector associated with a different feature. And to evaluate the decision tree, we're starting from the root. We're going to look on the index and the threshold, and we're going to take the value in the input that associated with this index and compare it to the threshold. So for example, for the root, we're going to take A3 and compare and check whether it's greater than 0.2. If A3 greater than 0.2, we're going to continue to the right child. And if A3 is smaller or equal to 0.2, we're going to continue to the left child. And do the same. Compare the value in our input in the index indicated in the node with the threshold indicated in the node. And by the comparison, according to the result of the comparison, we go either right or left until we'll reach the node, one of the nodes. And our prediction is exactly the label that's written in the node we reached. So if we do some representation manipulation, we will see that the only operation in the decision tree evaluation algorithm that it's not addition or multiplication is this comparison that happens in the leaf, in the nodes. So it's enough if we'll manage to actually convert this comparison to an equivalent sequence of additions and multiplications, Then, if we'll do that, we will be able to evaluate the decision tree on data that is encrypted, on encrypted inputs. So that's what we're going to focus in the rest of the talk, in the couple of next slides. So what is this comparison that we're doing in each node? It's a step function. What is a step function? It means if given an input x, if x greater than 0, and then f of x equivalent to 1, and otherwise f of x equivalent to 0. This is a step function where the step is at 0. What we're doing at the nodes is we have the threshold indicating where the step is. The threshold is the step. So this is the basic building block in decision trees, this step function, but it's not comparable with homomorphic encryption because it's not additions and multiplications. So what we're going to do is to approximate this function using a polynomial. A polynomial is a sequence of additions and multiplications. And what the polynomial would give us is the following. Instead of having f of x exactly 1 or exactly 0, we will have the guarantee that f of x will be very close to 1 if x is greater than 0, and otherwise it will be very close to 0. So we have a polynomial g that, given an input x, g of x would be very close to 1 if x greater than 0, and very close to 0 otherwise. And if we want to evaluate it, if we want the step to be, instead of in 0, to be in a threshold theta, like in the nodes, in the decision tree, then we are going to evaluate this polynomial g on x minus theta. And it will give us a value very close to 1 or very close to 0. Okay, and I want to say that this can be done because g is a polynomial and consists of addition and multiplications. We can do this over encrypted x. So what we do, we take x is our input, we subtract from it this theta, and then we evaluate the polynomial, which is just additions and multiplication, and this is comparable with homomorphic encryption. So the remaining question is how we did this approximation to give us a good result. So what we did is we picked a degree n and found a polynomial of degree n that minimizes the error that is close to the step function. And we used another trick. We did not just found the polynomial that minimizes the error, but we did a weighted approximation. We put weights on the x-axis such that close to the threshold, close to the step, we will have small weights, and further from the step, we will have bigger weights. And this gave us the ability to approximate with good accuracy the step function, but maintaining the degree of the polynomial as low as possible. And this significantly improved the efficiency of our algorithms. So what we get eventually, we tested it for different degrees, and eventually we use the polynomial that is marked here in yellow. It's a polynomial of degree 16, and the window, what we have here, different windows, it indicates how we spread the weights along the x-axis. So to summarize all of this, to combine what we saw, so to evaluate a decision tree over encrypted data, all we need to do is to evaluate in each node the polynomial g on the encrypted input and take the result and continue to evaluate it repeatedly on the nodes. Eventually, we will get a weighted sum of the labels of the leaves, and in order to get a single prediction, we will need to take the max over this weighted sum of the leaves, and that's how we get a final prediction. So to summarize, what we saw is that it's possible to better protect the data by using homomorphic encryption and performing computation over the encrypted data and without giving permissions to decrypt the data. And we can do it for decision trees as we saw today, but it is possible to do it also for logistic regression and also for neural nets. We implemented our algorithms and published them as an open source on GitHub, so you can take a look. And another important thing that I want to mention is that this enhanced privacy is not for free. The running time is slower than, of course, operating on clear text, but also there is a storage overhead if we'll do a naive approach and store all the data using homomorphic encryption. And we actually resolved the storage problem in a follow-up work that was published last year. And we managed to actually have a solution that stores the data using classical encryption. And on demand, only when the data is needed, we can securely transform it into homomorphic encryption. So we don't need to pay the extra storage because the homomorphic encryption ciphertexts are very long compared to classical ones. And another thing that we saw is that there is a trade-off between accuracy and performance. As, for example, in the approximation of the step function, we needed to have it low degree to be efficient, but also we needed a very good accuracy, so that eventually the decision tree using this step function, approximated step function, will give us results that are the same or very close to the results that the decision tree, the classical decision tree, would give us. Thank you.